Everybody doing? Hopefully you guys all had a nice weekend, had a good night's sleep, all that kind of stuff. So why don't you guys just all tell me who all's here, what kind of questions you guys have before we get started, and then we will jump into the homework. So let me just see. What's going on? Any stories, anything going on here? Let me see. Could you remind everyone about my message to the class over Google Classroom, that they should respond to my question if they want to be added to the new group chat? Yeah, so there's, I guess this is what you're talking about, but there's a new group chat. I don't know if I even read this morning the details of that, but Snowy Links, who is that? Is that Adam? Hey, morning. So I think Adam was organizing a group chat with physics just so people could discuss the homework and different stuff like that, so they could help each other. Yeah, and so if you're interested in that, which is obviously going to be useful to you guys, if you're interested in that, just talk to Adam. Make sure you give him a text and see, how do you join that group and all. Okay, so make sure you guys look into that and check out Google Classroom. We post, or students and me, we all post different messages there, so you guys can follow those messages. And I announce about homeworks and tests, all that kind of stuff. So make sure you guys check out Google Classroom. We've got all the different news that's going on right there. Okay, so anything else before we get started with the homework that we're going to be doing today? All right, so we're looking at today going over pendulums, and we're going to continue talking about springs today. The overall idea for these spring systems and the pendulum systems is that these are going to be examples of simple harmonic motion. Now, of course, they're not exactly like simple harmonic motion. You always are going to be having a little bit of damping, or maybe a lot of damping. Damping is that force, like friction, that's going to slow the process down and eventually stop it, right? But for the most part, we can look at these systems and consider them as types of simple harmonic motion. So you have a repetitive motion that can be essentially, you can use a simple equation to model this simple motion, this simple back and forth or cyclical motion. Okay, so last time when we were talking about pendulums, we said that we could actually look at a few different factors and relate them all to t, okay? And we said t is going to be equal to 2 pi. And it's not, surprising that pi is in there, right? Because we're dealing with these cyclical processes, and pi's got to do with circles, right? 2 pi square root of L over AG. And let's pause and think about, well, what is everything here? T, what is T? T, well, it looks like it could be a time, and it is. So T is the time for one complete cycle, and that's known as the period. Okay, that's the time of one complete cycle. And soon we're going to be talking about the frequency. I don't think we're going to get to the frequency really today, but we related and we said that the period is the inverse of the frequency, right? L is going to be the length of the pendulum. And then A sub g, that's going to be the acceleration due to gravity. Okay, and so most of our problems from the homework were a lot like the sample problem, I believe, and you were actually not solving for t, but you were solving for L. And so last time we said, okay, we're going to need to rearrange this equation so that we can properly solve for L. All right, and so I'm going to do that one more time today, and then we're going to solve problems 1 to 3, which is all pretty much a lot like the sample problem. And then we're going to solve number 4, which isn't too bad either. So I don't even think I'm going to need to go through all of these problems. So some of them I'll just give you guys the answers for, because there's a lot of similarities between 1, 2, and 3. And then I believe 4 has A, B, and C, which are all pretty similar too. Okay? It's a little unfortunate that the book didn't have you guys take any of these. At least I didn't remember that the book didn't have any of these pendulums on, let's say, the moon or something like that, because that would then change your A sub g. But I don't think any of the problems did, as far as I remember. Okay, so let's look at this. If we're going to be solving for L, right, we want to get L all by itself. And so to do that, probably the first thing to do is to divide both sides by 2 pi. So that's going to get you t over 2 pi equals the square root of L over a g. Then we need to take care of that square root, so we got to square both sides. And so we can put that in parentheses and square it, but let's just go ahead and square everything there on the left. That's going to get us t squared over 4, right? 2 squared is 4. 4 pi squared equals, and then that squared is simply going to be L over AG. And then from this point, all you do is multiply both sides by AG, and that's going to get us an equation for L. So that's going to be t squared AG over 4 pi squared equals L. Okay, and let me push that up a little bit. Okay, so that's the equation that we're going to use for numbers 1, 2, and 3. Let's go ahead and open the book here. I believe this is on page 605. And you guys should have all done that. And sorry for, I posted it. It was posted in Google Classroom as an assignment, but I didn't actually have it available for you guys to upload. So sorry about that. You can upload now on Google Classroom. And I made the due date a little bit later just because of that little glitch, okay? So if you were having problems, you're like, where do I upload this to? It's now available on Google Classroom for you guys to upload to, okay? So, number 1, we have the period of a pendulum in the preceding sample problem. So obviously, just like the sample problem. So the period in the sample problem is now going to be 24 seconds. How tall would the tower be? And in the sample problem, what was it? It was like 12 seconds. So if it's 24 seconds, what are we thinking? Is this going to be a taller tower or a shorter tower? So you might want to be thinking about that first, okay? And so we can notice that the period and the length of this pendulum are going to, they're not directly proportional, but as one increases, the other is going to increase. So as the length increases, the time is going to increase. As the time increases, the length is going to increase, right? Now it's going to, the length is going to be increasing more than the time, so we expect a very large increase in the height of this tower based on that, okay? So let's go ahead and plug in some numbers here. For number 1, let's see, we'll do it right here. For number 1, we have L equals t squared, AG over 4 pi squared. And so in number 1, you have a time of 24 seconds. So that's going to be 24 seconds squared times AG. Everything here is in Earth, so it's 9.81 meters per second squared. And then this is all over 4 pi squared. So we can just do the whole thing in your calculator. No need to do it stepwise. Okay. So that's going to be 24 squared times 9.81 divided by, and you could put the whole bottom in parentheses, which is probably the best way to do it, or you could just do multiple divisions. So this is going to be 4 pi squared on the bottom. Okay, and that is going to be our answer, right? 143 meters. That's pretty high for some kind of tower, right? 143 meters. Notice how here second squared over second squared cancels out, and we're left with meters as our units. Okay, so any questions on number 1? Any questions on number 1? All right, now number 2, number 3 are going to work exactly the same way, right? So notice that in number 2, and let me just pull my iPad over here so we can see it together, okay? In number 1, 2, and 3, we're all solving for the same thing. So, right, so for number 2, it gives us a time there of 1 second, and it says how long should the pendulum be. So once again, we're solving for L. In number 3, we have a trapeze artist that swings in simple harmonic motion. Once again, we have the period. That's our T value. Calculate the length. Once again, we're solving for L. So 2 and 3 are going to be done exactly the same way. So what we're going to do is I'm not even going to go through plugging in the numbers. You guys can plug in the numbers, and I'll just share the answers with you. For number 2, you guys should be able to get that it's going to be 0.2485 meters, or if you want that in centimeters, that's going to be 24.85 centimeters. Number 3, that's going to be 3.59 meters, okay? And they're all just the same kind of thing, plugging into this equation, just changing that period, and that's it. Okay, so questions on these. If you guys have any questions on 1 to 3, I'm just going to pause before I go on to number 4, because number 4 is a little bit different. Anything at all you guys can think of? Hopefully you guys got those. All right, so number 4 is, let me just bring this up, and A, B, and C are going to be exactly the same thing, okay? Oh yeah, so actually number 4, I misspoke earlier. Number 4, we are changing the A sub G. I thought there were, I didn't remember that, but here we go. So for number 4, oh, question. Can I round 2 to 0.249 meters? Yes, you can. That would be perfectly fine. Okay? In fact, it would probably be better to round it. So if you have only 2 significant figures, it would probably be best to round it to 0.25. But the reason I didn't round it is because we're designing the thing. And when you design something, you're not doing the significant figures thing, but you want to make this as precise as possible when you design something. That's why I left it as 4 significant figures. But again, I'm not going to be picky at all about significant figures here, so that's fine. All right, so number 4, what are we doing? We're going to calculate the period and frequency. Oh yeah, and so we get the frequency too. So we have the formula for the frequency of a 3.5 meter long pendulum at the following locations. So what's the same here is the length, and then the different acceleration due to gravity is going to be changing. Notice that they're really all 9.8, and so when we use 9.81, it's really kind of a joke because very few places are exactly going to be 9.81. So 9.8 really is the acceleration due to gravity on Earth, and then it's going to vary a little bit based on where you are. It's going to be greater at the poles because the poles are going to be closer to the center of the Earth, and then as you go closer towards the equator, it's going to be a little bit less because you're a little bit higher up. Okay, so with that said, let's go ahead and solve one of these, and then I'll give you guys the answers for the others. So for number 4, we have the same equation, right? So we have the equation T equals 2 pi square root of L over AG. And the only thing that we're going to be changing is that AG. So in A, so for A, we have the North Pole. So it's going to be, your period is going to be your 2 pi square root of, what was that? 3.5 meters in the top and 9.832 meters per second squared on the bottom. Okay, and so this answer is going to get, so you have meters over meters are going to cancel, and the per second squared is going to come to the top here, and you're going to end up with just seconds, and that'll give you the period. So let's plug in the numbers. 2 pi square root of 3.5 divided by 9.832. And that's it, right? And so our answer for A is going to be this. 3.74, and I'm just going to round this up to 3.749 seconds. Okay? And so you do the same thing for B and C, and let me just write down the numbers there. For B and C, I'm getting 3.754 seconds, and C I'm getting 3.758 seconds. Is that right? I think so. Okay, and that's our period, but also the question asks us to calculate the frequency. Now the frequency is going to be 1 over the period, or the period is going to be 1 over the frequency. So they're inverses of each other. And to solve this, let's just solve it for 1a. All we do is just 1 divided by that, or your calculator might even have one of these fancy inverse buttons. So you just, all I need to do is just literally press one button, x to the minus 1, hit enter, and there we go. I now have the frequency for 1a. Okay, so there's 1 divided by that, or the inverse button, is going to get you the correct answer. And let's do those in a different color. Let's do those. Let's do that in red. And that's going to be 0.266, and that's going to round up to 8. Now the question is, what are the units? Okay, and you could literally use more than one different units, possible units for this, and so it would be perfectly fine to make your units inverse seconds, right? Because if these are seconds, and then you do the inverse of it, so that you could just have inverse seconds as the units. Alternatively, most people like to have a unit itself rather than having an inverse units, and so that's going to be hertz. And so you could instead put 0.268 or 668 hertz as the units. Either one is fine, okay? So what a hertz is 1 hertz is 1 inverse seconds, or it can be defined as 1 cycle or 1 wave per second. Okay, so that's a hertz. And so we're going to deal with hertz a lot for this particular chapter, which is our basic unit for frequency. Okay, so you can solve for the frequency for both of these. You just do 1 divided by that, you're going to get the frequency. 1 divided by that, you're going to get the frequency. And I can just share my answers with you guys. For B, I got 0.2664 hertz, and for C, I got 0.2661 hertz. All of them are fairly similar, and we would expect that because everything's on Earth, so you're not going to have a big difference. If we went to the moon on this or something, that would be huge. That would be much, much different for these. But it's all on Earth, so it's going to be pretty similar. All right. So that's it for the homework. I don't think I need to go into any more detail for B and C. They're really done the same way. So if you guys have any questions, go ahead and ask now. And if not, A is actually 0.2667, if I'm not mistaken. I think I just did that, and I'm pretty sure I put it in right. So yeah, it's really close call, right? It's a really close call, and it depends on whether you rounded first or not. So if you notice in my calculator, right, I used this number and I took the inverse of it, and I got 0.26675. So really, really close call. but we're going to generally take the 5s and round up. So I'm going to say 0.2668 should be the correct answer, but really no big deal. All right, if you put 0.2667, really, really close. Yep. All right. So guys, any other questions on those? All right. So today we're going to continue looking at periods and frequencies of these simple harmonic motion systems, but we're going to switch back and do the springs again. Okay? So we already have gone over the concepts of the springs. We just need to have one new equation for the springs, and then we're going to solve the next day's problems, which shouldn't be too terribly bad because you guys already did the A and B, and so this is going to be kind of similar. Okay? So once again, if we have some kind of mass spring system, right? So let's say we have some kind of table here, and on top of the table we're going to have some kind of thing with a spring, and the spring is going to be attached to a mass. Okay? All right. So if everything here is fixed except for that mass, what we're going to do is we're going to take that mass, stretch it out, or compress it, and just let it go. And it's going to go back and forth, back and forth, back and forth. Obviously, if there's friction, it's going to slow down. That's the damping force. But if there's no friction, this is going to go on forever, right? Friction, there's going to be friction between the mass and the table. There's going to be friction inside the spring itself, and that's going to cause it to slow down and eventually stop. But in this system, if there's no friction, it's going to go on forever. We're going to call that simple harmonic motion. So we've looked at this. It's going to work in terms of if you have a vertical spring, if you have a horizontal spring, it's all the same, right? The only difference with a vertical spring, which is what we talked about before, is that gravity is going to cause the equilibrium point to be pulled down further. That is literally the only difference. So if you have a vertical spring system, gravity is going to cause that to be pulled down more, but otherwise it's exactly the same. All right, it'll just affect that equilibrium point, nothing else different. So it turns out that we have a very, very similar equation for these spring systems as we did for the pendulum. And let me just give you guys the equation. If you want the derivation, you can look at the book, but I just want to give you guys the equation. And it's an equation for period once again. And the nice thing is, because you guys are taking the test online, that you guys, it's all going to be open notes, so you don't have to worry about memorizing these equations. These equations are very, very similar, and you can get them confused, but you don't need to, because you can look up the equations, right? And so you can have your own equation sheet. It's best to have your own equation sheet. That's better than always going back to the book to look. But anyway, here's the equation. So you have the period is 2 pi times the square root of m over k. It practically looks exactly like the other equation, right? It looks like, and let me just even pull up the previous equation for the pendulums, right? So for the pendulums, we had the period is 2 pi times the square root of L over AG. This is going to be the square root of M over K. So it's the exact same format for the equation, just slightly different thing here and here. And let's identify what those are and try to make some sense of it before we solve a problem with it. M is going to be already labeled right here. This is going to be the mass that's attached to the spring. We're going to assume the spring is essentially massless, or at least this mass of the spring is going to be nothing compared to that, right? And K, that's going to be your spring constant. The same equation is going to work if this is, let's say, some kind of rubbery or elastic material too. Should work in a similar fashion, but springs are a little bit nicer because they're nice and stiff, and they can go back and forth a lot better. But you can do the same thing if you imagine, let's say, a vertical attached rubber band. It should work in a similar fashion. So what does this tell us? What does this tell us about this system? It tells us that the larger the mass, well, what's the mass going to do? In the previous case, for pendulums, the mass was both acting as increasing. So if you increase the mass, you can increase the force because the force was gravity. and also the mass was resistive because the mass was your inertia. But in this case, the mass is not going to contribute to the force at all, and so the mass is only going to contribute to inertia. Which means that the larger the mass, the slower it's going to go. The larger the mass, the slower. Let me even write that down. Larger mass equals slower. Why? Because the mass is inertia. The mass is resisting the motion. Okay? And we can see right here in this equation, as you increase the mass, the period is going to increase. Right? As you increase the mass, the period is going to increase, and the period is how long it takes for one complete cycle. Okay. Next up, we have down here in the bottom in the denominator the spring constant. And the spring constant tells you essentially how stiff the spring is. So, if we have a larger value of K, that's going to be a faster spring system, okay? So as you increase K, that's going to decrease your period, which means it's going to go faster, right? It's on the bottom. So as you increase K, that's going to decrease the period. So we have everything we need to know to go ahead and solve the sample problem. If you guys have any questions, go ahead and ask it here, as I'm going to skip over only a couple pages over to page 607 for the sample problem. Oh, and the sample problem here is a unique one. It does deserve going over here. It's kind of interesting. So you guys can go on page 607 to find the sample problem. Right? And I know the book goes through it, but I want to go through it too because it's quite interesting. So what do we have? It says we have a body of a car, and the car has a mass that is 1,275 kilograms. Okay, so a little bit over a ton. And it's supported on a frame by 4 springs. Okay, so we have 4 springs, which makes sense, right? We have one for each tire. And we're going to, well, let's continue on. We've got 2 people riding in the car that have combined mass of 153 kilograms. So what we can go ahead and do is, because that's the combined mass of the people, we're just going to add on that 153 kilograms right here. All right? When driven over a pothole in the road, the frame vibrates with a period, here we have the period, of 0.84 seconds. For the first few seconds, the vibration approximates simple harmonic motion. Obviously, after that, there's going to be damping. Find the spring constant of a single spring. Okay, so this is a little bit tricky because we have 4 springs and we want to get a spring constant for a single spring. Now, in order to solve the problem, we do need to make a couple of assumptions. And first of all, we need to assume, and I don't think it says it here, we need to assume that these 4 springs are identical, right? Because if they're different, obviously we have no way of telling which ones are stiffer and which ones are less stiff. And so that's kind of a necessary assumption. All right, once we do that, we can kind of work this out to our favor and kind of just figure this out, okay? So if we assume that these are all identical, what we're going to do is we're going to assume that each spring is going to hold an equal part of the car's mass. So each spring is going to hold 1/4 of the car up. And so to do that, let's go ahead and get the total mass of the car, all right? So the total mass of the car with the people is going to be 1,275 plus 153. And I'll go ahead and write that down. That's 1,428. 1,428 kilograms. But we want to get the mass of each spring. So we're going to take that number and we're going to divide it by 4 for each spring. So we're just going to go divide by 4, and that's going to get us 357 kilograms. Okay? So 357 kilograms is effectively the mass that's held or carried by each spring. Mass on each spring. Now, what about the period? Should we divide the period by 4? Would that be an important thing to do too? So we divided the mass by 4 because we have 4 springs and each spring is going to hold 1/4 of the mass. But should we divide the period by 4 too? Or maybe multiply the period by 4? Should we do anything like that? And the answer is no. We want to leave the period the same. Why? Because the period is the same for each of the springs. What do I mean? So that when that car is vibrating up and down, each of the springs is going to have exactly the same period. It would be impossible for them to have different periods, right? Each of the springs is going to have exactly the same period, and it's going to be 0.84. So we don't need to modify that. That is the period for each of the springs. That's the mass attached to each spring. Now we can go ahead and solve for K, all right? So it gets a little bit tricky if you don't make those assumptions, but once we do that, we have a value for M, we have a value for T, so we can go ahead, back up to this equation, and we can solve for K. But once again, this is going to be a little bit of annoying to rearrange that equation. So let's rearrange the equation, then we can plug in these numbers, and before we forget what everything is, let me go ahead and just make a note. All right, this here, that's going to be our T, and this here is going to be our M. All right, so we have this equation right up here, and let's even, let me see if I can conserve paper here. Let's do it up here, okay? So what I want to do is I want to rearrange this equation to solve for K, because that's what we want to solve for. So I want to get K all by itself. So the first thing I want to do is divide both sides by 2 pi, just like we've done before. So this is going to be T over 2 pi is going to be the square root of M over K, right? Okay, so divide both sides by 2 pi. Once we divide both sides by 2 pi, now like before, I want to square both sides. So that's going to get me T squared over 4 pi squared equals M over K. Now, this is a little bit annoying because we have K on the denominator, and so you might be tempted to just divide both sides by M, but that's going to mess you up, right? If we divide both sides by M, you're going to get 1 over K here, not K, okay? So in order to do that, we need to get K on the other side of the equation, and there's a number of ways to do this. Like I said, you could just divide both sides by M and then take the inverse of that. We can cross multiply, or we can multiply both sides by K, divide both sides by all that stuff, and either way is going to work, okay? Let me just take the cross multiplication away because that's going to get us, that's going to get rid of these fractions. So that's going to be K T squared, right? So this side is going to equal M 4 pi squared, or 4 pi squared M, however you want to do it. Then all we need to do is divide both sides by T squared. So K is going to be M 4 pi squared over T squared, okay? And that's the equation that we're going to be using to solve for K. So once we have that, we can just plug in some numbers. And so let me actually go back to here, and I'm going to rewrite it down here. So K is going to be, and let's just rearrange it to 4 pi squared M over T squared. Let's plug in some numbers, and that's going to get us 4 pi squared times the mass of 357 kgs over 0.84 seconds squared. Plug in the numbers and we should be able to get the final answer. Hi. All right. So 4 pi squared times 357 divided by 0.84 squared. We don't need parentheses on the bottom because the order of operations is going to do the square first anyway. And that's going to get me my final answer, which is pretty big. And you stop and pause and say, okay, should it really be this big? Does that make sense? and you think to yourself, well, this is a car. So yeah, of course it's going to be a big number because you're going to have really, really stiff springs. You can't use some kind of really soft or weak spring in a car. So it makes a lot of sense, right? And so our answer is 19. So this is 19,974. What are the units? Does anybody remember the units for the spring constant? Units. Okay, so you have kilograms per second squared, but what's that going to turn into? That's going to be newtons per meter. Okay, so newtons per meter are going to be the units for the spring constant. If you write kilograms per second squared, that's going to be okay. That's fine. It's just not the normal way that you write the units for a spring constant. Okay, and you can round it off if you want. We legitimately shouldn't have that many significant figures here, but I'm just going to leave it and just, I'm just going to go with it. Okay, but we have 19,974 newtons per meter, and that's going to be the spring constant for each spring. So we are all done today. Does anybody have any questions before I sign out? All right. By the way, this particular chapter is not going to take us too long. I'm thinking of a test probably next Monday, okay? And once again, I'm thinking a similar kind of test, not super long, maybe let's say 4 or maybe 5 free response questions. And the free response questions, you're not going to have any multiple choice questions. It's going to be only free response, similar to the last test. And expect that to be next Monday. So we will finish up the chapter, let's say by Wednesday, and then we'll have some time to review after that on Friday. But we're going to be, wrapping this chapter up and having a test next Monday. Okay? So if there are no questions about anything, I'm just going to close out. Have a nice rest of your day. Have a great week and all that kind of stuff. Stay safe, stay healthy, and stay sane.